Hello everyone. In the last video, we studied how to simulate the half-controlled converter, or you can say semi-converter. In this, there are two SCR and two diodes connected to the AC supply, and how it works on a DC, convert AC into DC. Last time we said this alpha is to 30 degree. Now you can set alpha according to your requirement. Now I'm setting alpha is equal to 60 degree, and let us one more time simulate the given circuit. So let me save it and run the simulation. So you can observe here, I'm getting for alpha is equal to 60 degree. I'm getting the output voltage, output current, source current. I have formatted the my scope window using the style, and everything is you can adjust according to your color requirement. So whenever next time we simulate it, it will display like this only. Now we want here the RMS values and average values of all these. So to get the RMS value and average value of all signals, so I'm taking once again from block. So let me shift this from block on downside here. Here I'm going to take the VS first, source voltage first. Sorry, by default I clicked in VS. So I have taken the value of the VS. I want the mean value of this. So for taking the mean value, so you have to use this mean block. Okay, so here the minimum frequency is the 50 hertz. Okay, so you set this frequency is to 50 hertz, but mean value should require absolute value, not the positive and negative value, because a positive and negative value in AC cycle will get cancelled with each other, and average will be displayed 0. So that's why you take a absolute block, so it should not be a 0. Then you connect this absolute block with this, connect this block with this. I need RMS value also, so RMS value I'm taking. So RMS value, I will connect this block RMS value of here, and at output I need to display it. Okay, so let us take a display. Display. I will connect this first here, and I will copy this display, and I will display over here. So let us run this file. So see, our RMS value was 230. So why I'm getting 239 here? Because I have not set this frequency to the 50 hertz. Set this frequency to 50 hertz, and we do know the initial RMS value is 230. You can set it to 230, so it will faster converge. In mean value already I have set it to 50 hertz. Now once again run it, so you can observe now this voltage is equal to 230 volt, and this is equal to 207. Okay, so these two are correct voltage. If you calculate the RMS value of the RMS value 230 already given in the problem, but if you take the average value of that given RMS value, it comes to, so how to calculate the average value? RMS value is 230. For a sine wave, form factor is 1.11. So divide it with 1.11, you will get average value. So I'm getting the 207 as the average value, which I'm getting here. Now we know that this block is required everywhere. So I will keep this display apart. Uh, and what I will do, I will disconnect this, and just I will connect this terminal with this terminal. Okay. Now I will copy this two block, right click it, and I will create the subsystem from this. So from the first you will get the mean value, and from the second you will get the RMS value. So see, here you will get a mean value and RMS value. So I have connected the signal one. Here I will get a mean value. Here we will get the RMS value of the source. I will keep the display apart. Now I will copy the same. I will paste it here. Now here I want the average and RMS value of the V0. So I will type it V0. Now I will copy this two times. Here I need the current I0, mean value of the current output current, and RMS value of the output current I0. Then on this side I need the mean and RMS value of my source current IS. Okay, apply. Okay. Now I want to combine all these values. So I will take a mux over here. So how many inputs I have to set to this mux? 8 inputs I will set. Hmm. Let me increase the size of mux. So first this is connected, then this is connected. Sorry. Okay, one by one, you can click this block and click to this, it will connect. So all signals are combined together. If you want, you can further increase the size. Then you can connect a single scope here. I will delete this another scope. You can connect this single scope. Now you can run it. Okay. So here you can observe, if you increase the size of the scope, you can observe the first one is the RMS average value of source voltage, average value of RMS value of source voltage, average value of output, RMS value of output voltage, average value of RMS output current, RMS value of output current, average value of the source current, and RMS value of the source current. Okay, so you can observe here these all values. Now what I want from this, I want to calculate the power. Okay, AC power and DC power. So how I can calculate the AC power and DC power? Let's see. uh, for a power, what is the formula? Let me write down first the formula. If I want the DC power, so DC power you will get as V0 into I0. And if I want the AC power, PAC, then it should be V0R, RMS voltage into RMS current, I0R. So let me increase the font size of this to, I will make it 18. Okay, now it is visible on your screen. I want to simulate this thing. So average, first two is the multiplication of average value. So here I will take this sign of product. Okay, take the sign of product. Here you connect first V0. V0 means output voltage average value and output current average value. Okay, here you will get the DC output. Now take the copy the same product block. Here you connect the RMS output voltage and RMS output current. Here you will get the AC power. Okay, so I need the rectification efficiency also. So I will take a block of divide. AC power DC power divided by AC power will give you the rectification efficiency. I will take one more block of display. I will take mux also. Okay, input to this mux I will set it to 3. Let me increase the size of this mux. Here I should get a rectification efficiency. Here I should get a DC power, AC power. Here I should get a AC power, and I want to display it. Now once again run it. Okay. So after running it, you can observe this rectification efficiency I'm getting at a 0.562. DC power is 2344 watt. AC power is 4172 watt and rectification efficiency is 0.562. Keep in mind it is the rectification efficiency. It is not the efficiency of the converter. Okay, it is the rectification efficiency. By this way, you can implement this power block. Okay, so the given power block you can implement. So let me shift this block. I will select this by arrow. I can shift. This is implemented over here. Okay, I have implemented these equations here. So this is what about the measurement. Through this measurement, I can take the readings of the simulation, and your calculations and simulations you can verify it with this. So then this is in this simulation we have performed for R load. Now let us consider that instead of R load, it is the RL type of load where inductance is of zero point 0.5 Henry. Okay, so it is given in the problem the inductance is of zero point 0.5 Henry is added. So when the inductance of zero point 0.5 Henry is added, so see the first our voltage is, so see the current inductor opposes to the rate of change of current, hence the current increases slowly, but it is not coming at the constant value. So let me increase the simulation time to observe this. I'm simulating up to 1 second, and let's check what output we'll get. You click to this scope, you will observe here the current is becoming steady state here. So current is approximately 15 ampere steady state. And if you observe the source current, okay, so let me take the this one for zoom. You can observe my source current is almost a square wave in nature. Whereas DC current is a constant DC, but AC voltage is not going to the negative side as in the fully controlled converter. Okay, so in the fully controlled converter with RL load, the DC voltage is going towards the negative side. So I want to observe the FFT of this signal. So double click on Power GUI block, go to the app, click on FFT analyzer. So it will open the FFT analyzer, but signals will not shown. I will show you how to get the signals at the output. Okay, so you can see here the list is empty. Why this list is empty? Let me shift this on downside. Okay, I will minimize, or you can, I will close this FFT block. Come to the your scope. I have not stored the result of this scope. Then you go to the simulating parameter, go into the logging. I want to save this data as a scope data uh, array. I want to store with the this data as an array. Okay, so store this data as an array. I will give this name as HC half source converter. So I will give the name as HCC. Okay, HCC, I have stored with the name of HCC. Now again run it. Okay, sorry, this is not supporting for array, so I have to store with the structure with time. Again, double click here, go to in the Simulink, logging, instead of array, stored as a structure with time. Apply, okay, close it, once again run it. Okay, so this data is recorded now. You can observe in the scope of you can observe in the scope with the out name. Here in this out Simulink, you can see the HCC where time and signals are stored. Signals are stored. Source voltage, output current, source current with its values are stored. But still, you cannot perform the FFT with this. Why we cannot perform the FFT? Let's check. If I double click to the Power GUI block, then go to the app, click to the FFT analyzer. Here again you can see the list is empty. I was searching for this reason from a long back, but the answer was very simple. I have to go into uh, here. There is one more in a MATLAB command window. When you come to this command window home, here there is, you can say, preference. You click to this preference. In this preference, you will find one command with the, just a minute. Okay, so how to get the signal into FFT block? That is, I want to see the harmonics and THD. So go into the Simulink. So go on the right hand side bottom where your solver is there. Go click that OD23TB. go into the setup. Here, go into the data import output. Here it is a single simulation output with the out variable is appeared. You unclick this. Okay, so you please unclick this single simulation output, then apply. Okay, now once again come to the simulation and run the file. Okay, let the file is to run. Okay, now it is run. Double click to this Power GUI block, then go into the app FFT analyzer. Okay, now you can see signal is appeared there. Okay, previously signal was not there in FFT analyzer, but I want to see source voltage. I will start my starting time. Late waveform is to be at a steady state, so zero point 0.6 cycle, zero point 0.6 second to I will take 5 cycles in the calculations. Okay, my frequency, fundamental frequency is a 50 hertz, and if I ask the compute FFT, so and I want to display only FFT window, so I can change this zoom signal as FFT window, so only FFT window will be displayed. See, THD is 0% because source voltage is a pure sinusoidal. Now if you see the source current, okay, THD is to be observed only at the source side. Okay, and if I click on the compute FFT, you can observe 30% are the THD in the current. That is, current is not a sine wave. Current where you are getting it is just like a square wave. Okay, Cauchy state wave. You can say Cauchy square wave. You are getting the current as a Cauchy square wave. So that it is not fixed. If you want to see the in form of list instead of bar, you can click to the list. Okay, and again you can say the compute FFT. So the DC signal is 0%, fundamental is 100%, second harmonics is 0, third harmonics is 2%, fourth harmonics is 0, fifth harmonics is 20%. Likewise you can see, or if you want with the harmonic order only, so you click on the harmonic order. Okay, and again I will click on the compute FFT with bar plot. Okay, I want the harmonic order. See, fundamental is 100%, third harmonics, fifth harmonics, seventh harmonics. So fifth and seventh harmonics is the dominant. It is a six pulse, so -1 +1. So these are for a six pulse. Sorry, for the three for the single phase half control converter in the source current, you will observe that fifth and seventh harmonics is the very large. Then 11th harmonics, then the 13th harmonics is very large. So likewise you can observe, if you want to see the list of this, then again click to the compute FFT. You can see the THD and everything into this window up to the 19th harmonics it is recording. So now if you want to see in terms of ampere, then you can click here and again say the compute FFT. So it is showing in ampere, 16.9 ampere at an angle of 31 degree. Second harmonics is 0, whereas third harmonics is 0.39 at an angle of 40. Fourth harmonics is 0. Fifth harmonics 3.4 ampere at an angle of 27.2 degree. So likewise you can list out the harmonics. You can export this graph also. Okay, so this is about the simulation of half control converter. Hope you like it, and how to simulate it or semi converter. You can check it for various alpha. If you want, I will make this alpha is equal to here, even 150. Alpha is equal to 150. Let us simulate it for alpha is equal to 150. Okay, run it. See, the graph current is reduced because out voltage is reduced, so you can see only this much current. Sorry, uh, you can, if you zoom this much window, you can observe the only this much voltage is available at the output. So the small current, hence the average current value is also decreases in that case. Okay, so by this way you can simulate the half control converter. I hope you like this video. If you like this video, kindly subscribe my channel, share with your friends. Thank you.